Hello students, it's Dr. Mink, your professor for this course, and welcome to part 2 of chapter 3. We're going to start with section 3.3, which is entitled More About C++ Loop Statements. We will get to a very detailed level on building loops, designing loops, terminating loops, etc. Let's get started. This slide helps define some terminology we'll use in referring to loops. A loop is a tool, or in this case a program construction, that repeats a single statement or a sequence of statements, blocked statements, a number of times. The body of the loop is the statement or statements that are repeated, and each repetition of the loop is called an iteration. Some questions you should ask yourself when designing loops. What should the body be? What code has to be executed? Multiple iterations. And then the second question is, how many iterations should the body be executed? How many times should the body of the loop execute? A major difference between the two loops we've explored so far are that a while loop checks the Boolean expression at the beginning of the loop, and if that expression evaluates to false, the loop may never be executed. Whereas a do-while loop checks the Boolean expression at the end of the loop. So even if the Boolean expression is false, the do-while loop, the body of the loop, is always executed at least once, because the Boolean expression checked to determine whether or not to continue looping or whether or not to loop again is at the end or after the body. Let's take a look at the syntax. Here we have the syntax of the while loop, and below it the syntax of a do-while loop. Each is shown with a single statement body and a multi-statement body. So let's just take a look closely at the while loop. While, then a Boolean expression is evaluated, and there's the single statement, or within braces, a block of statements to be executed if the Boolean expression returns true. So if the Boolean expression returns false, the statement or block of statements within the loop are never executed. Whereas a do-while, whether it's a single statement or a block of statements within braces, you have the do, and then you have the statement or statements, and they're automatically executed the first time before we get to the while followed by the Boolean expression. So even if the Boolean expression the first time it is evaluated returns false in a do-while, the body, the statement or block of statements, has already been executed a minimum of one time. This is the defining characteristic of a do-while loop as compared to a while loop. A while loop has the potential to never execute the body of the loop, the single statement or block of statements. That happens when the expression immediately, the Boolean expression immediately following the while statement is evaluated as false the first time through. The do-while will always execute the statement or body or series of block of statements a minimum of one time. Now we're going to take a look at a live coded solution or demonstration for a while loop with a single statement body, a while loop with a multi-statement body encompassed in the braces,
Here's the single statement, no braces, and a do-while loop with a multi-statement body and a do-while with a single statement body. So what I'm going to do is I'll put breakpoints at the first statement in the body of each loop, and we'll run it to the breakpoint. I'll initialize y, the char variable answer with y, and we have int count equals 1. Do you want to run the loop? Yes. And I have a few watches. Answer equivalent to y, true. Count less than 3. Count is currently 1, it's true. Get a little real estate here. And the compound Boolean expression, answer is equivalent to y and count less than 3 is true. So this first loop, this is true. And we're going to execute the single body statement. Notice this is not part of the body. Count gets reset. Here we go. Count equals 1. Count equals 2. Count gets reset to 0. This is the second statement. And here we are. We're down in the second while loop, which has a body. So each time count goes to 1, count goes to 2, we execute the entire body, both of these statements. Okay? Now we're in a do while loop, right? With a multi-statement body. 1, 2, there we are. Do while. And here we are executing a single statement body for a do while loop. 2. Count equals 0, count equals 1. And then we're done. Now what happens if we initialize answer to no, anything other than y? Okay, well, let's see. We skipped the body of the single statement while loop, and we went right to this as a second statement. That's not part of it, and we reset the counter to 0. So a while loop, the minimum number of times a while loop can run is 0. If this is false, if the compound Boolean expression is false, it's going to run 0 times, which is this case. Now let's go to the next one. Executing a multi-statement body for a do while loop, count equals 0. This is the second statement. There can be more. How come, even though this is always false, we got that output? Because in a do while loop, right, a do while loop runs the body of the loop before it encounters or evaluates the Boolean expression. So the minimum number of times a do while loop will run the body is 1, even if the initial evaluation of the Boolean expression that determines whether or not to iterate again is false. And here we have that again here. So what you have is, in this example, and I can put this code in Canvas, you have an example of a while loop with a compound Boolean expression and a single statement body, a while loop with a compound Boolean expression and a multi-statement body, and the same for a do while loop. I strongly encourage you to download this, put the breakpoints and the watch points in and run it so you understand the mechanics of this.
The increment operator, plus plus, for which C++ is named after, has significant use within loops. We've seen it so far to increment an operator in a statement such as number plus plus to increase the value of the variable number by 1. The increment operator can also be used in expressions. Here's an example. Int number equals 2, so declare and initialize number as an integer holding the initial value of 2. And then we have a statement, int value produced equals 2 times number plus plus. Now, let's talk about how that actually works. Is this, the right-hand side of this assignment statement, is it 2 times 3? In other words, is number plus plus incremented and then multiplied times 2? Number plus plus first returns the value of number to be multiplied by 2, then increments number to 3. Because the plus plus is behind the variable name, the increment takes place after the expression is evaluated and before the next line of code. This is a somewhat abstract concept that you're going to have to get used to. And it's difficult to grasp at first and can be very, very confusing. So if this expression were int value produced equals 2 times plus plus number, it would be 2 times 3 because the plus plus would be a postfix versus would it be a prefix versus a postfix incrementer. And we'll see more of that moving forward. Here's more detail on the post and prefix incrementers. Number plus plus returns the current value of number, then increments number. So if it's in an expression, the value used in the expression on that line is the current value of number, and then it increments number. And an expression using number plus plus will use the value of number before it is incremented. Plus plus number increments number first and then returns the new value of number. An expression using plus plus number will use the value of number after it is incremented. Number has the same value after either expression. In other words, the following line of code, number will be incremented by 1. The prefix plus plus number or postfix plus plus number determine what value of number is used in the expression when it's called. Pre and postfix increment operators make for some great brain teasers. Here's two comparisons, starting with a postfix operator and then a prefix operator. In the first example, we start with the int number equal 2, then int value produced equals 2 times number plus plus. So in that equation, in that second line of code, number returns 2 to the expression and then increments number. So if we have cout value produced is 2 times 2, or 4. And then we output a space, and then number is 3. Remember, on the line after, whether it's a pre or a postfix operator, it's always incremented by the next line. Now, the second example, int number equals 2, int value produced equals 2 times plus plus number. So plus plus number will return the incremented number to the expression it's called in. So that will be 2 times 3. So that will be 6. Int value produced is assigned a value of 2 times 3, which is 6. So we see out value produced 6 space 3. See, number in each of these examples, whether or not you use pre or postfix in the previous line, is always incremented by the time it gets to the last line of this code. Here's an example of a program, a fully developed program, that asks the user how many items he or she ate today, takes that number in as number of items via CN, and then it loops that number of times. So if the user says 7, it will loop 7 times, and it uses a postfix increment operator in the Boolean expression to control the loop and also to increment the counter. So the first time it comes through, count equals 1, while count plus plus less than or equal to the number of items. So in this dialog that we see at the bottom, it was 7. So 1 less than or equal to number of items, and count is also incremented to 2 after that statement. So they input the calories for item number 1, etc., etc., etc. And then it comes back up, and count, by the time it loops, is 2, and then it's 3, and then it's 4, and then it's 5, and then it's 6, and then it's 7, but it's still true because 7 is less than or equal to number of items. So it loops 7 times, it increments count to 8, and then the next time it comes up to the while statement, that's false, and it skips over. This is a very, very nice way to code a counter, and also to keep track of the number of loops while incrementing the counter within the Boolean expression. Take a close look at this. I've given you the code for this in the timeline. You can download this, run it, play around with the numbers, change that postfix to a prefix, and see what happens. But I strongly suggest that you experiment with this. It's an important concept. The decrement operator works similarly to the increment operator, only instead of increasing the value of the variable by 1, it decreases the value of the variable by 1. So you've got a counter that's counting down if you use it as a counter. Here's an example. Int number equals 8. We declare number as an integer, and its initial value is 8. Int value produced equals number minus minus. That is a postfix, post meaning after, postfix decrement operator. So int value produced is going to, the first run through this is going to equal 8. And then number will be decremented, decreased by 1, before the next line of code. So cout value produced will equal 8, and then a space, and then output number will equal 7. Replacing number minus minus, a postfix decrement operator, with minus minus number, a prefix decrement operator, would display, given the same code, 7, 7. The minus minus number would return the decremented number first to the expression, and then also to the next line of code. Now, my friends, we're going to introduce a new loop mechanism in C++. It is the for statement, or for loop. It's designed to accomplish some tasks such as adding numbers in a given range. It is sometimes more convenient to use than a while loop. However, it doesn't really do anything that a while loop cannot do. I'll show you the syntax and a for statement in use in just a minute. This slide shows a direct comparison of code implemented with a while loop and then the same requirements implemented with a for loop. And as you can see, the for loop contains the initialization of the counter, the max value for the counter, the upper boundary in this particular case, and less than or equal to 10, and the incrementer within the expression of the for loop. So the while loop, while n less than or equal to 10, with the statement sum equals sum plus n, and then n plus 1 blocked within the loop, become simply one statement, sum equals sum plus n. So the counter, the incrementer, and the upper limit are all handled within the for loop's expression. This makes for a compact program solution, especially if you have a single statement for the body of the loop, or you're calling a function, which we'll get to later in this class. This slide focuses on the individual components of the for loop. You have the for statement, and then within the expression you have the initialization action, n equals 1, the Boolean expression, n less than or equal to 10, and the update action, n plus plus. If you really want to get compact with your coding of a for loop, the for loop can also include a variable declaration and initialization in the initialization action. Here, in the previous for loop we looked at, n would have had to have been declared as an int prior to hitting the for loop. In this case, it doesn't have to even be declared. It's declared during the initialization action. So we have for int n equals 1, which was previously n equals 1, with a prior declaration, n less than or equal to 10, n plus plus. So the initialization creates a variable n of type int and initializes it with a value of 1. Continues to iterate the body as long as n less than or equal to 10, and it increments n by 1 after each iteration. We'll look at a comparison of the for loop and while loop syntax next. This slide shows both the syntax and a coded example of a for loop, for statement, and the equivalent syntax and coded example for the same requirements using a while statement or a while loop. The big difference is that in the coded example of the while statement, number, which is the counter, has to be initialized prior to the statement, whereas the initialization is incorporated into the for loop. The output's the same. It's the old 100 bottles of beer on the shelf, blah, 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 take one down. So you'll see the output will be 100, 99, 98, etc., decrementing by 1 until it gets to 0. The initialization and update actions in for loops often contain complex expressions. Here are 3 examples where the update is not a straight n plus plus or an increment by 1. And the third is obviously a very complex example, and you'd have to really know what you were doing to use an example like that. Take a look at it. This can be done, obviously, given the requirements of a loop. That's how it would have to be done. Just like the do and the while loop, The for loop body can be a single statement, or it can be a compound statement, a block of code enclosed in braces. Here's an example. The loop body statements could be 2, 10, 50 lines of code. However, if it becomes a long body of statements, the suggestion, which we'll explore later in this course, is to build a function for the body of the statements. But we're going to get to that in a few chapters from now.
Next, we'll take a look at a demo that illustrates the difference between a while loop and a for loop. For loops are very convenient when you have a counter, because a for loop can have a built-in counter. But a for loop really can't do anything more than a while loop can. It's just a little bit easier, it's more compact. So let's take a look. So here we're starting off with int count equals 1. So I need to declare and initialize a counter if I'm going to use it in the while loop. So we'll output first a while loop demo, while count less than or equal to 5, and then the body of that loop is just going to be two statements. Cout count equals, and output the counter and an end line, and then we're going to increment the counter with the plus plus increment operator. So we'll start with 1, go to 2, that'll be true, 3 true, 4 true, 5 true, 6 false, and we'll end. Then we have the for loop. The for loop has a built-in local variable counter. I can declare a counter right in the for loop. So our counter is going to be I, integer I. We're going to start it at 1. Our Boolean expression, I less than or equal to 5. Pretty much the same as count less than or equal to 5. And I plus plus will be our increment operator. And we're just going to simply output count equals I. And there's no need to do any incrementing or decrementing. That's all taken care of. So if I run this, I have a few watch statements here. So count less than or equal to 5. Notice I is undefined at this point in time, because I is a local variable that only lives within the scope or the body of the for loop. So here we have true, true, I is 4, I is 5, it's still true, and there it's false, so we're done. Now we're into the for loop. I less than or equal to 5 is true because I starts at 1, 2, 3, 4, 5, still true. We're going to go into the body of the loop, output, and then it goes to 6 and it becomes false. I'll also place this code in the timeline in Canvas for you to run yourself, put the breakpoint and the watch points in. This is excellent practice for you.
Here we see both the syntax and a coded example of a for loop with a multi-statement body, a block of statements to be executed as the body of the loop, and they are enclosed in brackets. As I mentioned earlier, if this gets too unruly with too many statements, later in the course I'll show you how to write a function that you would call within the body of the loop. A semicolon creates a C++ statement. Placing a semicolon after x++ creates a statement x++, semicolon. Placing a semicolon after nothing creates an empty statement that compiles but does nothing. You're probably thinking, why is he telling us this? This makes sense, but why would anyone do this? Because it leads to a very common mistake made by beginning programmers, which I'll show you in the next slide. I just saw this error 2 nights ago in a traditional C++ class, and the student was racking his brain to try and figure out why this was not working. Placing a semicolon after the parentheses of a for loop creates an empty statement as the body of the loop. See the first line in the example? That semicolon should not be there. If you put it there accidentally, it does not recognize hello, new line. It will print one hello, but not part of the loop. The empty statement is the body of the loop, and then the hello, new line is output once, not 10 times as intended by the designer of this loop. So be careful not to put that semicolon after the parentheses of a for loop, the beginning of the for statement. The ANSI standard for C++ compilers requires that a variable declared in the for loop initialization section be local to the block of the for loop. So int count equals 1 creates an integer named count that is only accessible within the body of the for loop. If you want this code to be portable, don't depend on all compilers to treat these variables as local to the for loop, because there have been some differences in compilers. Now, to answer the question, which loop to use? Sorry, I'll leave that in. I have the option of re-recording this, but I'll leave that in because it was comical. You don't choose the type of loop early in the design process. First, design the loop using pseudocode. Translate the pseudocode into C++. When you're translating it into C++, it typically makes the choice of an appropriate loop much clearer. While loops are used for all other loops where there might be an occasion where the loop should not run. Remember, a while loop might not run even once. Do-while loops are used whenever the loop must always run at least once. For loops are favorable for situations where numeric calculations are being done, especially when using a variable changed by equal amounts each time the loop iterates. If you have a condition when a loop is encountered, but because of a condition prior to you getting to the loop, the code containing the loop may return, the while statement, the Boolean statement may return false, and the body of the loop may not be executed even once. That is the perfect criteria for a while loop. Now remember, a for loop can do the same thing as a while loop and vice versa, but a for loop typically contains the initialization of the counter in the for loop statement. So that big difference is the while loop depends on a value of the counter that's set by the main program before the while loop is encountered, not as part of the loop as it is with a for loop. So you want to think long and hard about using a for loop in a condition where you may never have the loop execute, the body of the loop execute, because of a condition that exists before you get to the loop. The most obvious reason to choose a do-while loop is when the loop body must be executed at least once. And that's a guarantee with a do-while loop, because the condition which determines whether or not the loop will iterate 2 or more times is not encountered until the body of the loop has been executed at least once. There are times when you want to put a premature exit in a loop. For example, if the body of the loop checks for invalid input, that would create an inappropriate or bad calculation, it is often best to end the loop with a break statement. The break statement is used to exit a loop before normal termination. You want to be careful with nested loops. Using break only exits the loop in which the break statement occurs, and we'll take a look in a second. Here's a program that sums 10 negative numbers. It clearly asks the user to enter 10 negative numbers, using a while loop to calculate the sum. But it also has an if statement that makes sure each number input is is less than or equal to 0. So if a number entered is greater than or equal to 0, it gives output or a positive number, or 0 is entered as etc., etc., etc. And then it has a break within the body of the if statement. That break breaks the while loop. When it breaks the while loop, it tells you the sum of the numbers that were correctly entered until it encountered the error. Take a close look at this. It's very important that you understand how this break statement works. Here are a few brain teasers for you to try. If you have any problem, let me know. But if you paid attention to the content and understood the content that we just covered, these should be easy for you to solve. Give them a try. Let me know how you make out. The next section, 3.4, which is the last section in Chapter 3, covers designing loops. We will explore the criteria you should examine when designing loops within a program. The design of any loop should include 3 major considerations: the body of the loop, what will actually execute each time the loop increments, the initializing statements, including the counter, and the conditions for which the loop will end. Loops are commonly used for sums and products. Reading a list of numbers and calculating the sum or product of those numbers. The pseudocode for this task might be sum equals 0, then repeat the following this many times, see in next, sum equals sum plus next, so the value being read in each time gets added to the sum, end of the loop. This pseudocode can be easily implemented with a for loop, as we'll see in the next slide. Here we have the code implemented from the pseudocode on the previous slide. Notice that sum must be initialized prior to the body. When you're summing, you initialize what I call the holding variable, in this case sum, to 0. But if it's product, if it's multiplication, that can't be 0. It has to be 1. Because the first iteration would be, let's say the name of the variable, the holding variable is product. It would be product equals products times next. Well, if product starts out at 0, it will always yield 0 and will not do the multiplication. This is very commonly used code. Take a good look at it. A for loop is often your best choice when you enter the loop with a predetermined number of iterations. And if you remember the pseudocode, it include the phrase, repeat the following this many times. So the example would be for int count equals 0, count less than or equal to this many. That would be the predetermined number of iterations, and then your counter increment, and then followed obviously by the loop body. Here's the for loop for a product. Very similar to the example given earlier for a sum. The main difference is that the product must be initialized prior to the body of the loop, and it must be initialized to 1, not 0. I explained that in the previous slide, but I'll do it again. If product was initialized to 0 the first time through the loop, product equals product times next. Well, if product is 0, the new product will always be 0, and you will loop and loop and loop and loop and still have 0 as the product, because anything times 0 is 0. So just beware of that. There are 4 methods commonly used to terminate an input loop. They are list headed by size. That's when we can determine the size of the list beforehand. Ask before iterating, which is when you ask if the user wants to continue before each iteration. If you've ever used an ATM machine, after you've executed a transaction, it asks you if you'd like to complete another transaction. Yes would cause the loop to run again. No would exit. List ended with a sentinel value. That's when you're using a particular value to signal the end of the list. I've seen input prompts that tell the user to enter a series of positive numbers, and to end the list, enter a negative number, and the sentinel value would be anything less than 0. Running out of input uses the end of file function to indicate the end of a file has been encountered. Although we haven't covered file stream input and output yet, so we'll be talking about that in general terms. Let's explore each of these methods now. The for loops we've been exploring provide a natural implementation of the list headed by size method of ending a loop. Here, in this example, we prompt the user how many items in the list, and we use an int named items to hold that value, and then count less than or equal to items is used as the method of ending a loop. So we know beforehand, before we enter the body, the size of the loop, or the number of iterations of the loop. This is called list headed by size. Ask before iterating is often implemented with a while loop. Here, the last 2 statements in the body of the loop are a prompt asking the user if they wish to continue. In this case, it's a cout. Are there more numbers? Yes or no. And then the user inputs a y or an n. And then it goes back up to the Boolean statement, and the Boolean statement is while ans, ANS, equals y, or lowercase y, continue. So if the user were to, at any point in time in the loop, enter an N as in Nancy, the next time the loop came to the condition, the Boolean condition, it would stop the loop. Here we have an example of a list ended with a sentinel value. We're using a while loop, and while number is greater than 0, number is being input using cin. The user is prompted to enter a list of non-negative integers. I'm not sure why the author chose non-negative. Wouldn't you just say positive integers? And then place a negative integer after the list. So each time the body of the loop is processed, the last thing that happens is a new number is implemented or taken from the keyboard. We go back up to the while statement, and if that number is positive, or in the case of the author, non-negative, the loop increments again. So when this loop encounters, from cin, it encounters a number, a number entered from the keyboard that is negative, the loop stops. So the negative number is the sentinel value. Since we haven't covered file stream data, all the data that we've input and output has been using cin or cout, the keyboard and the monitor. This won't look familiar to you, but we're using a while loop to check that we haven't achieved or reached the end of file. And this is for reading data from a file as opposed to from the keyboard using cin. Next, we'll cover 3 methods to control any loop. Count control loops, ask before iterating loops, and exit on flag condition loops. And a lot of the concepts covered here in control will be the same as termination. Count controlled loops determine the number of iterations before the loop begins. The list headed by size is an example of a count controlled loop for input. The next is exit on a flag condition. Loops can be ended when a particular flag condition exists. This would require a variable that changes value to indicate that some event has taken place. And this is called the flag. Examples of exit on a flag condition is the list ended with a sentinel value, when the input value turns negative, which is the example we covered 2 or 3 slides previously, or when the flag is the EOF, end of file character, that indicates all the data from a particular file has been read in and we're at the end of the file. This slide describes a caution to be used with an exit on flag loop. So here's a loop that is used to identify a student with a grade of 90 or better. Actually, if implemented correctly, it would output student number and his or her grade if it were greater than 90. There's a problem with this code. Take a close look at this. Let's say there are 24 grades that were input and read by the loop. Think about the possibility of having no students with a grade of 90 or better, or more than one student with a grade of 90 or better. Let's take a look at some possible solutions, or patches, if you will, to fix this. I jumped the gun telling you the problem. That's okay. I've obviously done this before. The loop on the previous slide might not stop at the end of the list of students if no student has a grade of 90 or higher. So it is a good idea to use a second flag to ensure that there are still students to consider. We'll look at a revised version of that code on the next slide, which shows a better solution. Here's an example of an addition to that code that uses an AND operator and a second Boolean condition, n less than a number of students. So the condition evaluated to determine whether or not the loop is while grade less than 90 and n less than number of students. If that compound statement becomes false, see out no student has a high score. Okay, students, now we get into a very fun topic, nested loops. The body of a loop may contain any kind of statement, including another loop. It's called a nested loop. When loops are nested, all iterations of the inner loop are completed for each iteration of the outer loop. Give serious consideration to making the inner loop a function call to make it easier to read your program, and we will cover functions in a short period of time. That's a topic we'll get to in Chapter 5. Display 3.15, which is on the next slide, shows two versions of a program with nested loops. Let's take a look. Okay, students, here we have a fully implemented and coded example of a nested loop. Notice we have a box drawn around each loop. The while loop is nested within the for loop. The while loop is terminated by a sentinel value, which is a negative integer. The for loop is a list headed by size, and we know the number of reports to be generated before we enter that loop. Take a good look at this. Notice the while loop will fully implement to however many iterations the user enters until that hits that sentinel value. For each iteration, each single iteration of the for loop, the while loop will completely iterate till it terminates. When you're debugging loops, you should look for these common errors. Off by one errors in which the loop executes one too many or one too few times, often associated with using greater than when you should have used greater than or greater than or equal to, or using less than when you should have used less than or equal to, or the opposite. Infinite loops usually result from a mistake in the Boolean expression that controls the loop, and it doesn't stop. The loop continues infinitely, which causes a problem, obviously. Off by one errors are very, very common with loops. So check your comparison. As I mentioned earlier, should it be less than versus less than or equal to, or the opposite? Check that the initialization uses the correct value. Should you be starting at 0? Should you be starting at 1? Does the loop handle the 0 iterations case? How does the loop react if there's 0 iterations? Infinite loops can be a problem. Sometimes you have the wrong inequality. You're checking for greater than, and you should check for less than, and the loop just continues to increment. The counter just continues to increment in a way that's not being checked. Try to not use equality. Try to not use equality, because if let's say you're using integers and your incrementer is incrementing, your counter is incrementing by 2, and you start with an odd number and you're looking for numbers less than 12. if you start with an odd number, 1, 3, 5, 7, 9, 11, if you said equivalent to 12 to terminate the loop, you will jump right over 12. If you say less than 12 or less than 13, you will catch that. So be careful using equivalence. Tracing is a technique for watching a value change during the execution of a loop. Some systems include utilities to help with this. It's really easy. Just use the cout statement. You can see out the value of your counter or other variable that's being used to control the loop each time in the loop. And I usually put cout test of counter, and then I cout the actual value of the counter, and it'll generate a lot of output, but then you can see each time through the loop what the value of the variable actually is. The next few slides will take us through a debugging example that has what I consider to be a very common mistake in it. The code is supposed to conclude with the variable product containing the product of the numbers 2 through 5. So 2 times 3 times 4 times 5. It looks correct in that int next equals 2 and the product equals 1, while next less than or equal to 5. And then you've got the incrementer, the counter, if you will. Product equals product times next. Let's take a look. Before you hit the advance button, take a close look at this and see if you could determine where the problem is. It would be useful for you to take a long, hard look at this before advancing to see where the problem is. In this slide, the programmer uses tracing in the form of cout statements to trace the two variables that are being manipulated within this loop. Cout next equals next, product equals product, and each time through the loop, that will be output, and you'll be able to trace the value of those as the loop iterates. So tracing those variables would show actually two problems, but the cout statements that we added as tracers show that the loop never multiplied by 2. Well, this is an easily solved problem. We incremented next before we calculated the product, the first run of the loop, the first iteration, when next equals 2. 2 was never added to the product or part of the product. We started off with product equals 3 times next. So, I'm sorry, product equals 1 times next, and next was 3 at that point in time. So we moved the incremented next behind that calculation. But there's still a little problem, and we'll fix that next. Retesting shows that the loop never multiplies by 5. Why? Because we terminate it when next was less than 5. So when next was 4 and then increments to 5, it comes back up to the while statement, and 5 was not less than 5, so that was false. It never went and multiplied product times 5. The Boolean expression should have been next less than or equal to 5, which would include 5 in the product. This slide contains some very, very useful loop testing guidelines. Every time you make a single change to a program, it must be retested. You should not make multiple changes and then retest, because you won't know what caused what. Changing one part may require a change to another. Every loop should at least be tested using input for the following conditions: 0 iterations of the loop body, 1 iteration of the loop body, 1 less than the maximum number of iterations, and the maximum number of iterations. These are called boundary conditions. And last but not least, sometimes it is easier to throw out a very buggy program and start over. The new program may be easier to read, the new program is less likely to be buggy, so you may be able to develop a working program faster than if you repair bad code, especially if the code you're debugging was not written by you. That concludes section 3.4 and chapter 3. Here are some little brain teasers for you to consider. Help make sure that you've achieved the learning objectives for 3.4. Can you describe how to trace a variable, list possible solutions to an off by 1 error, and determine the number of fence posts needed for a 100-meter long fence? I'm assuming there's a fence post every meter. And there is a boundary condition issue there that, well, think about it.